Demonstration problem. A 2-kilogram lamp is attached to the ceiling of an elevator with a cable, as shown in the picture. Part A, if the elevator is moving downwards at a constant speed of 20 meters per second, what is the tension in the wire holding the lamp? The tension in the wire is the apparent weight of the lamp. To solve the problem, we need to identify the forces on the lamp and use Newton's laws to solve for the tension. There are two forces on the lamp. One's a contact force by the rope, or the tension force, which acts upwards on the lamp. The other is the field force, which is the gravitational force exerted by the earth from the center of the earth on the lamp with no contact. To solve part A, we note that the lamp in the elevator is moving with a constant speed in a straight line. It's moving downwards. We recall what Newton's first law says. If velocity is constant, then the total force is zero. This is a vertical or a y-axis problem only. We can rewrite that as if v sub y, the velocity in the y direction, is constant, as it is. It's a minus 20 meters per second, with the negative direction being downwards. Then F net of y, the total force in the y direction. We go to our free body diagram, our force diagram, to see what the net force in the y direction is, what the forces are. We have the tension force F sub t, which is upwards or positive. We have the weight force F sub w, which is downwards or negative. So F net of y is F sub t minus F sub w, and this is equal to 0 by the first law. Solving for the tension force, which is the apparent weight of the lamp, we see that it's equal to the weight force, or mass times gravity, substituting 2 kilograms times 9.80 meters per second, and this is 19.6. We recall that a kilogram times a meter per second is a newton. So what we have found is that the lamp moving downwards in the elevator at a constant speed, or its apparent weight, is exactly the same as it would be if it were just sitting in a room not moving at all. In part A, we had that the tension, or the apparent weight of the lamp, was just the actual weight. This was a consequence of Newton's first law, which says if the velocity is constant, then all the forces are balanced, or the total force is zero. This meant that the tension was in magnitude the same as the weight, so the apparent weight was the actual weight. Part B, the elevator is now accelerating downwards at 2.5 meters per second. What is the tension, or the apparent weight of the lamp in the wire holding the lamp? We again draw the forces acting upon the lamp, and once again we have the field force of the weight force, or the gravitational force, a non-contact force, which acts downwards. Tension force, or the supporting force, acts upwards, and that's the apparent weight, and that is what we need to solve for. The givens are a sub y is minus 2.5 meters per second. Along an axis, and this is a y-axis problem, the direction is given by the SIGN. The acceleration is in the negative y direction. The mass is once again 2 kilograms, and the magnitude of the acceleration of gravity is 9.80 meters per second. It is also negative because it acts downwards. Recall that Newton's second law says that the total force, or the F in F is equal to ma, must act in the direction of the acceleration. Since the acceleration is in the negative y direction, the net force in the y direction must also be negative. The equation, Newton's second law, or F vector, is mass scalar times acceleration vector. This is a y-axis problem, so we write the second law along the y-axis. We write total force in the y direction, or F net of y. To see what that force is, we go to the force diagram. And so the total force on the lamp in the y direction is the tension force, which acts upwards. So that's plus F sub t, plus a minus weight force, since it acts downwards. So minus the weight force, and that's equal to mass times acceleration in the y direction. Solve for the tension force, so we algebraically rearrange. We get the tension is the weight force plus m a sub y. We substitute in for the weight force being mass times the acceleration of gravity. We get mg plus m a sub y. We factor out the mass, and we get mass times the acceleration of gravity g plus a sub y. Substituting in, we get that the tension, which is the apparent weight of the lamp, is 2 kilograms for the mass times g is 9.80 meters per second, plus the acceleration, which is plus a minus 2.5 meters per second. This gives us that the tension force, or the apparent weight, is 14.6 newtons. Compare this with the actual weight. The actual weight is F sub w is mass times the acceleration of gravity, or 2 kilograms times 9.80 1.80 meters per second, or 19.6 newtons. The apparent weight for the lamp in an elevator that's accelerating downwards is 14.6 newtons, which is less than the actual weight of 19.6 newtons. Remember that in part A, the velocity was constant, and so the acceleration was 0, which meant that the total force, F net of y, was balanced. It was equal to 0. The tension, or the apparent weight, was the actual weight. In part B that we have here, the acceleration is not 0. The velocity is not constant. The total force is not equal to 0. It's equal to mass times acceleration in the y direction. And that gives us that the tension force is not the weight.